While working with booleans and integers as a hoot and a half, let's go ahead and add support for some additional data structures in our language. First up are strings. These are going to be the same strings that we can find in other languages. We will be able to bind them to identifiers and pass them along to functions. The only operator that we will need to support with strings is the concat operator. To get this started, pop back into the lexer package, and the idea is that our lexer, when it sees a string, will return the whole string as a token. First up, add a new string type to the token types. Then, add a case to our switch statement inside of the getToken method inside of the lexer. The readStringHelper method that you see here is pretty easy. In this method, we mark the position we start at and we progress until we reach the closing quotation mark or reach 0. Then we just return the slice of the input that corresponds to our start and end position. And that takes care of the modifications that we need to make to the lexer. Next up is to adjust our parser. To do this, the first thing we have to do is go into our AST package and define a node for our string. Let's call it string literal, and it will have two fields, a token and the actual value of the string. Of course, we will add the boilerplate for the parent node to retrieve the token lexeme and the string representation. Now head over to the parser package and register the string token in our prefix function map. Register it with the parseStringLiteralHelper method. The parseStringLiteralHelper method just creates a string literal object using the current token. Now we just need to head over to our evaluator. Inside of the object package, create a string object type. Also, add the string struct, where the only field will be a string named value. Then override the parent methods as well. The last step is probably the easiest. Jump over to the evaluator package and update the eval function to add a new case to handle these new string literal nodes. All we are going to do is return a new string object. Now we have full support for strings. Something we can now add is the concat operator. To do this, we just need to update our evaluateInfixExpression method to account for these string types. This evaluateConcatStringsHelper method is very simple. First, we just want to make sure that we are working with a plus operator, and then we will create a new string by sandwiching the values of the left and right objects together. Inside of this method is where you could implement string comparison as well, or any other operators that you would like to support. Next on the list of critical data structures that we need to include are arrays. Arrays will be interesting because we will have to add a new index operator made up of two brackets and an integer. To start, let's head over to the lexer and add two new tokens to our token types to represent the right and left brackets. Now just update the lexer to return a new token for our two new tokens. Then head over to the parser and we will learn how to handle these new tokens. First, go into the AST package and create the structure that is going to represent the array. All it is going to be is a list of expressions that we name items. Then override the parent methods, and the toString method is a little wordy, but it should be easy to follow. As you can see, this is essentially just a wrapper around a Go array. Next, head over to the parser package and register the left bracket token as a prefix function with a helper method called parseArrayLiteral. This method is pretty easy. We are delegating the heavy lifting to a new method called parseExpressionList. The parseExpressionList method will take an end token to know when to stop looking for another expression to parse. It will of course return a list of expressions as well. The first thing to do in this method is make sure that there are actually expressions to parse by checking that the next token is not our end token. After this, it just becomes a matter of parsing each expression, eating the commas in a for loop, and then we do a check to make sure that our end token is present and we return the list. You'll notice that this method is almost identical to the parseCallArguments method. You can replace that method with this one if you so choose. Just make sure to pass in the right parentheses as the end token. Next, let's add some support for the index operator in our parser. In order to do this, we need to accommodate the following form in order to pull an element from our array. On the left side, we have an array expression, and on the right side we have an expression that will evaluate to an integer. And first thing to do is to add a structure to represent this inside of our AST package. It will contain a left side expression and an index expression. Make sure to add the parent methods as well. Something interesting to note is that in order to parse this index operator properly, we are going to have to give it the highest precedence of all when parsing. So add it is another precedence level and update our precedence map accordingly. Like the call expressions for functions, the index operator will be registered with the infix tokens. And that, believe it or not, handles the parser. Now we just need to know how to evaluate them. Now go to your object package and add a new array object type. Then add an array struct with one field called items. It's really just a wrapper around goes arrays. Then override the parent methods. Next, head into the eval method in the evaluator package and add a case for the array literal. We're going to use the same method we used to parse the arguments from a call expression, and this should be pretty easy to follow. At this point, we can create arrays, but we still can't use them because we haven't finished up our index operator. And the only thing that you will need to do is add another case to the eval method. We will evaluate the left side first, which will result in an array. Then we will evaluate the expression for the index. This should evaluate to an integer. Then we return the result of a helper method. The helper method will be called evaluate index expression and will take the left side array and the right side index. First thing that we want to do is check to make sure that the data types align, otherwise we're going to throw an error. Afterwards, we extract the actual array from our node, we extract the integer value from the index node, and last we would determine the max value that our index can be for this array. We do a quick error check to make sure nothing is awry, and then we return the object in the array. Pretty easy. And with that, you should be able to use arrays and indexes anywhere in the code base. I hope with these two examples you can also add other data types to the language as you so desire. A good one to add is a hash map, and really you can just follow the pattern that we have established here with strings and arrays. That's all I've got for today. See you later.